Okay, so let us start with an example of uh, SVD. So what was SVD? Can you recollect what we were doing? So a singular value decomposition of a matrix is known as SVD. So you can see that this is the SVD is the final factorization of a matrix. So if someone asks you like what is the best factorization of a matrix, then you should tell the SVD is the best one. Okay, because you can do a lot of application, lot of things using SVD. Okay. So what it does to a matrix A? You can decompose this matrix A into three matrices, that is U, sigma, and a V transpose. Okay. I will tell you why we are writing V transpose at the first place. Okay. When? So can you tell me what is special about U? U is an orthogonal matrix. V transpose is also an orthogonal matrix. Okay. Sigma is the diagonal matrix. Okay. I hope you remember this. Fine. So A can be any matrix. In the decomposition, why SVD is so nice to use? Other QR method and all they need, isn't it? LU decomposition also needs A to be a square matrix. Yes, but SVD doesn't need your matrix to be square. It can be any matrix. It can be a rectangular matrix also. That's the beautiful part about SVD. A can be any matrix. Okay. So I hope you remember also this, that here, now we come to this statement here. Read this statement. Now, this is a statement which I am not proving and is your assignment. Okay. So this is a theorem, like, or a result you can say, that if a matrix A is like symmetric, you know what is symmetric? You also know, I think, positive definite. No? Try to see what is this. Okay, if your matrix A is symmetric and positive definite, then its eigenvectors will be orthogonal. Its eigenvectors will be orthogonal, and we can write the matrix A as A equals to, can you tell me? Yes, A equals to Q gamma Q transpose. Okay. Can you say how this is related to SVD? This is not using SVD, just using linear algebra. So if A is a symmetric positive definite matrix, then its eigenvectors will be orthogonal, and we can write the matrix A as A equals to Q gamma Q transpose. Can you see that when you compare this with SVD here, it acts like U, it acts like sigma, it acts like V transpose. So this is a special case. This is a special case of SVD, okay, without even applying. So this is a motivation why researchers thought that you can have a decomposition like this. And then they thought that can we generalize this? And they came up with this SVD decomposition. So I would tell you that since all the class is here, I would tell you that lot of new discoveries are made just by observations. Okay, many different things are around you. You have to observe, think from a different angle, see from a different angle to make something new. Okay, so this was already in linear algebra. This theorem is already in linear algebra before SVD was known. Then SVD came. Why SVD came? Because they know that yes, decompose matrix A into such a nice thing, Q gamma Q transpose. Then researchers thought, can we decompose any matrix like that? Okay, then researchers thought that yes, let us see, can we decompose like this? Then they thought, yes, can we write something like this? Then they derived it and got many results. Okay, so sometimes some things are already there. You have to look those things into a different way. That's what matters, to create some new knowledge. Anyway, so this is how I can motivate you to see SVD. It is not just a magic thing. Okay, so you can see that you can write like this. So this is your assignment for the next class. How are we getting this? Okay. So there are two assignment questions. Okay. Fine. Since we are not aware of this row space and column space, I cannot go too detail, but yeah. Consider this matrix A to be 4, 4, minus 3, 3. Hmm? Consider this example. P. Okay. Now, can we do a singular value decomposition on this matrix? Can this matrix be written in terms of U sigma V transpose? That's the question. Okay. We have just taken a 2 by 2 matrix because it is easier to compute the eigenvalues, singular values, and all these things. Okay. But if you work in Python, you can always scale up your matrix and find the SVD. Even you have a function SVD and you just pass that matrix A, it will give you all this decomposition. What is U, what is sigma, what is V transpose. We are just seeing what Python does in the background just by looking into a small example. Okay, can anyone tell me what we have to do here? What we have to do here? What should your first approach? Can you see into your notes and tell me? Hmm. Yes, yes, that's good. So we have to look into A transpose. Okay, then you will get the matrix U. Okay, you just write the eigenvectors as the vectors of this, like columns of the matrix U. Then you do A transpose A. If you do A transpose A, you can find V. So if you find U and V, it is done. Because you already know sigma, you can compute sigma. We'll see how. Okay, we'll see how. But let us start finding it. I think everyone remembers why we are using A transpose or A transpose A. Can you see into your notes? Can you go to your notes back and see why we are using A transpose A or A transpose? Mm-hmm. Got the idea why we are computing A transpose A? No? I think it is clear. I wrote it very properly, no? Okay. So you know that you need to compute A transpose A. Can you compute A transpose A for this? Step 1. Compute A transpose. What is A transpose A? Let me know. Yes? Tell me. Transpose A is a symmetric matrix, which I gave as an exercise, I think. Isn't it? Transpose A is a symmetric matrix. Okay. It's a symmetric matrix. Where you do the transpose, you will get the same. Okay. But mind me, A was not symmetric. Was A symmetric matrix? No, but you got A transpose A symmetric. So something is there, like, yes. Okay, anyway, so A transpose A is symmetric. Now I ask you to find the eigenvectors of this matrix. Find the eigenvectors. This is the second part. Find eigenvectors. And those eigenvectors are VIs. Okay. Can you find the eigenvector for this matrix? And I had told you that eigenvectors are the VI's elements, the vectors, and the eigenvalues of this matrix A transpose A will give you sigma i's. So those, they are giving you something related to SVD. So find the eigenvectors. So that the eigenvectors are correct or not. How? And therefore, the eigenvectors will be orthogonal. Okay, so what eigenvectors you will get, those will be orthogonal also. You can check it. Now, tell me the eigenvalues, please. Eigenvectors. Eigenvalues. Yes, 18 and 32. Eigenvectors. Okay, you call, tell me. From minus 7. Okay, then. Okay. Okay. That sounds odd. Yes, you will get 7, 7 maybe. So this 7, 7, you can treat it as 7, 1, 1 and 7, 1 minus 1. Okay. So therefore, you can also take these as eigenvectors. 1, 1 and 1 minus 1 as the eigenvectors. V1, V2. This is, yeah. Everyone understood? V1, V2, eigenvectors. Okay, there is a confusion. Okay, so you are saying that, yeah, maybe my writing, yeah. You are saying that this, right? Okay with you? So now can you say what is V matrix? Can you say what is V matrix? But before that, let me simplify something. Third step. The third step is you need unit vectors actually. You need unit vectors. So can you tell me how the unit vector should look like? V1 should be, so it magnitude is root 2. So divide by root 2. Okay. 1 by root 2, 1 by root 2, and there 1 by root 2 minus 1 over root 2. Unit vectors. So unit orthogonal vectors are known as orthonormal vectors. Okay. If orthogonal vectors are unit vectors of unit magnitude, they are known as orthonormal. So these vectors you will get now is orthonormal because their magnitude will be 1. And we need them. We need unit vectors. Okay, can you tell me what should be the matrix V? Matrix V is nothing but V1, V2. Isn't it? What is V1, V2? I mean unit vectors. Tell me. 1 over root 2, 1 over root 2, 1 over root 2 minus 1 over root. Am I correct? I think this we can keep it as V transpose actually. This is V transpose. So are you getting U sigma V transpose? You got V transpose. One factor you found out already. So this is, yeah, just treat this as V transpose. I meant to write the right hand side. Okay, V transpose is this, and you got this matrix. Okay, now I'm asking you, what should be, do you also have got the sigma matrix also? You also got the sigma matrix. What should be the sigma matrix? No, but remember, these are sigma i's. These are sigma I squares. These guys are sigma I squares. To get sigma i's, you have to take the square root of that. Eigenvalues of A transpose A is equal to is equal to the square of the singular values of A. Okay, so therefore you have to take the square root. This I have covered in the previous class. So you have to take the square root of 32. What is square root of 32? So here it should be root over of sigma 1 squared, root over of sigma 2 squared, 0, 0. So what is that? Root over 32, 0, 0, root over of 18. You mentioned me the eigenvalues correctly, right? The order is correct, right? Else it will be trouble. We can't use, if you're saying to me 32 root 32 here, the corresponding eigenvalue should be here. Okay, so root 32 is, I think, 4 root 2, 0, 0, 2 9 is 18, 3 root 2. Can you see that we already got V transpose and sigma? So what we have so far? So this guy, what is known for us? Let me write that. This you already know, this you already know. What is remaining? Matrix U, isn't it? How you will find matrix U? Yes, A transpose A. Sorry, A transpose. So this is the fourth step. This is the fourth step. Now we are going to the fifth step. Shall I go to the next slide? Still, oh no, okay. I can still go to the next slide by going not to the next slide also. Sounds good. Okay. You want to see up also. Okay. Shall we proceed? So, what is the fifth step? Can anyone tell me? Now, V and V transpose and sigma are known already. But matrix U is unknown. Still unknown. And we have to find that, right? We have to find that matrix U. How you will find it? Check your notes that we now took A transpose A. So now you have to take A transpose. Okay. If you take A transpose, it will help you to find matrix C. Okay. What is A transpose? 32, 0, 0, 18. Yes, great. Great. Can you see something very nice happening here? Yes. A very nice thing is A transpose turned out to be a diagonal matrix. And if it is a diagonal matrix, you can just say that the diagonal elements are the eigenvalues of that matrix. The eigenvalues are sigma squared. The eigenvalues are sigma squared. Eigenvalues, what you missed here is today is eigenvalues of A transpose, okay, is equal to eigenvalues of A transpose A, that is equal to the square of singular values, that is sigma I squared of A, matrix A. So in order to compute the singular values of matrix A, to find eigenvalues of A transpose A or A transpose. And if you take the square root of those eigenvalues of A transpose or A transpose A, you will get the singular values of matrix A. This is the catch. This is the most important concept. This is the most important concept. So this you can think of as sigma 1 squared 0, 0, sigma 2 squared. And this is actually lambda 1 and lambda 2 of A transpose. Then now you can see the connection. If you find the eigenvalues of A transpose or A transpose A, that will be nothing but the square of singular values of A matrix A. And you can see that previously also we got sigma 1, like eigenvalues were 30 to 18. Now also the eigenvalues are 30 to 18. You can see how this A transpose and A transpose A are so nice friends. Okay, they're helping each other out. Okay, so can you tell me the eigenvector of this matrix? That will be our U matrix, no? Eigenvectors. Eigenvalues you know now, 32 and 18, but eigenvectors of this matrix. Mhm. Hmm? Maybe, maybe. Okay, do this. I will share this note with you, hmm, for SVD. Here, I think SVD is most very nicely written, the note here. So I'll give it to you. Okay. And there, try to read this and see how you can write you, how you can find you. First step, find you. And second, convince yourself that by putting all this together, that is, after finding sigma, after finding V transpose, convince yourself that you are actually getting the matrix A. Okay. This is solved in the note. Next time, someone should explain me. Okay, this I will give it to you now. Hmm? Did I send you the notes for interpolation? No? It is in the notes, right? In the scanned notes. Can you see the scanned notes I have posted on Google Classroom and let me know what's the last? Otherwise, yeah. So we can, yeah.